There's no stapler up here.
Okay, let's get started. Just turn it in. Yeah. If you don't have if you didn't use a staple, what do you think I recommend you do next time? Staple it. Okay. Because Varun, who's sitting at the front here, say hi, Varun. So Varun is not very happy when staples don't exist on homeworks. Okay. So to make Varun happy, what should you do next time? Put a staple on it. What is he also not like? Homework's being turned in late. So if you have a homework, what should you do right now? Turn it in. So if you don't turn in your homework, should you expect it to be given feedback? No, possibly no feedback. So Varun can decide whenever he wants to pick up that stack of homeworks, and that's the final stack of homework. So if you have anything to turn it in now. Okay? So Varun can pick any time he wants to pick up that stack of homeworks. So I think it's safe now. Yeah, so go ahead. Okay, cool. So are there any questions about the homework itself? Yeah. So will we get it back before the test? Definitely not. Okay, no, I'm going to try. So I've instructed the grader to get all of the feedback to me by Tuesday of next week. I think the test is Wednesday. Yeah. Oh, Thursday. Okay, so either Tuesday or Wednesday, I'm not sure. But I asked to do it before the test. Yeah, so you should be able to get it back before then. If not, then maybe if the TA happens to have it, then you can ask the TA, oh, what's the feedback I got? And then the TA can send you.
So the homework answers.
Great question. So the homework answers, I haven't instructed the TA to write solutions for the homework, but if you bug him enough, he may be lenient and write solutions.
So we all send an
Yeah, and I recommend doing it all at the same time to inundate him with email. No, don't do that. So I haven't instructed him to do it, but he may be willing to do so. But if you have questions about the homework in terms of like if you want to see a solution done, you can ask them during class. That's fine. But I'm unless you ask him, I doubt that they're going to be made. Yeah. How's he going to grade the homework? Are homeworks being graded? Given feedback. So the TA and the grader are going to work out a potential sample solution on paper, or the grader will do it him or herself, and then the grader will go off of that. But it's not really, so the thing with this material is there's very rarely one correct answer, exactly one correct answer. There are many ways of approaching it. So like the third question on majority, there's no one way to get that answer correct. There are gazillions of ways of writing out the set, the majority set itself. So the grader's actually going to look at your reasoning and how you did it and see, oh, okay, the initial DFAs you worked with, you missed this transition, it should have went here instead. Or you missed in the product construction, you applied this transition wrong. So these problems are simple enough that they don't have to go off a solution here. So I don't know what they're going to do, but they're probably going to discuss like general ways of approaching it, but there's no one way of doing it correctly. Other questions about the homework? Yeah.
Can you get that sample solution that they're using and then put it on?
Again, I don't know if they're using one, but again, ask the TA because that's the person who would be responsible for that. Other questions about the homework? Any individual questions about the homework?
No questions about, yeah.
So when I was working on the concatenate or intersection of L1 and L2.
Yeah.
To short it down, there was. I'm trying to explain it in,
Yeah.
words.
Yeah.
But so for the bottom row of Q5 or R4, whatever it was, they weren't exactly similar, but they could loop back to each other, if that makes sense, of all 3, 0, 1, and 2.
Oh, okay, yeah.
If one didn't loop to itself, it looped to the other one. Would you
Yeah.
combine them?
Yeah, you would combine. So that's one thing that you could try to minimize is if you're at a state and there's no way at all from that state to ever get to an accept state, that means that connected component, you can think of squashing all of those states down into one state because they're all states that you can never reach a final state with. So if we had a situation like a state here that's not final, and then a state here that's not final, and then a state here that's not final, and then it loops back here, and there's no other transition anywhere else, then I can shorten that into this. That would be a way to simplify it. Another thing that you could do for minimization is if you have two states here, and let's assume that either they're both not final or they're both final, and they have the same outputs. So like the A transitions go to the same place, and then the B transitions go to the same places, then these states really do the same thing. Because it doesn't matter what I read previously. It only matters what this state is and what the transition is going to the next state. So then I could squash these down into one state that has the A transition going to the original place and the B transition going to the original place. If one of them was final, then I can't do this. Anyone can explain why I can't do it if one of them's final and the other one isn't? Well, if I can reach one, actually, here's a shorter reasoning. If I merge these states, what should it be, final or not final? Because if I reach the final state, that means some string led to the accept state and a different string led to the non-accept state. So if I merge them, then those two strings will go to the same state, but they disagree on whether it should be accepting or not. So therefore, it won't work if one of them is accepting and one of them isn't. But if they're both the same, then you can merge them. So it's just thinking along those lines, yeah.
Okay, so I had a question
about
homework. So there was this question that asked for a language, for a DFA, which language is like, first character is same as the last character.
Mm-hmm. Yeah.
See, like, I was trying to create a DFA, but I felt like the only way to loop out of it, like to create something random and then 1, 1 or 0, 0 or 2, 2.
Yeah.
Like I would have to use 2 to get in and then 2 to get out. But how could I make it?
Yeah. So here's the thing. So for that oops, I had the eraser on. So for the same character question, same character, first character as last character, same thing. So if I have the start state here, if I see a 0 first, is that going to be a different behavior than I saw a 1 first? Is that a different thing that I'm looking for eventually? Yeah. So if I see a 0 first, I better look for a 0 at the end. If I see a 1 first, I better see a 1 at the end. So I'm not going to do the entire solution, but let's just handle the 0 case. So if I see a 0 here, well, here's the first thing. What should the start state be? Should it be final or not? Yeah. What is the empty string? Is the first character the same as the last one? Yes. Yeah. Now you may argue and say, well, the first character, there isn't a character, so therefore it should not be accepting. Either one of those ways is appropriate. So it's just different ways of interpreting it. Again, English is terrible. But what about the state that I reach after I've read a 0? There is a character there. So the string that is just 0 and nothing else, is the first character the same as the last character? Yeah. So should this state be final or not? It should be final. Okay, well, so I'm looking for it better end with a 0. So if I'm in this state right here, and I see a 0, is the last character that I just saw a 0? If I read one more 0, is the last thing that I just saw a 0? Yeah, so what should I do on 0? Loop there. If I see another 0, does it matter? No, it doesn't matter, because it's just the last thing that I saw. What if I see a 1 or a 2? Oh, not loop out, but go to a different state. Yeah. So if I see a 1 or a 2, I better not stay in the same state, right? Because that's the last thing I saw. It doesn't match the first thing that I saw. Well, in this other state over here, what if I see a 0 in this new non-final state? I go back. Because if I see a 0 again, that's the last character I saw. But we already have a state that already determines that for us. What if I see a 1 or a 2 in that new state? It loops on that state because as long as I'm seeing 1s and 2s, I haven't saw the 0 that I need to see at the end. Okay, so that actually handles the 0 piece. And the 1 and the 2 pieces are almost identical. So you would just have a 1 piece that goes down here and a 2 piece that goes down there. And it's very similar here. So that's how you would do that one.
Okay, thank you.
Yep, yeah.
So the start date isn't the final stage.
What's there?
The start state
Yeah.
isn't the final stage.
Oh, yeah, so that's the thing that we were just talking about. It could be final or not depending on your interpretation of the question, because is the first character of the empty string the same as the last character of the empty string? You may think of it as yes or no depending on your interpretation. Here I made it so that since we said the first character, there is no character in the empty string, so it can't be accepting at that point. But you may say, okay, well, the start and the end of the empty string match, so therefore it should be accepting. Either interpretation's okay. Again, English is awful. You had a question? Or does anyone else have a question? Yeah.
Are you allowed to interpret one character as not being possible to say it's both first and last?
Yeah, so that's another interpretation. Again, English is horrible. What if you wanted the first and last character to not be the same place in the string? But here's a little harder to argue that because the first character is the 0 and the last character is that same character. So it's kind of hard to argue that. But again, you could interpret it that way. So yeah, that's why we have regular expressions for this. Other questions? Yeah.
So for L2, it says W contains at least one of 0, 1, 0, 2, or
Yeah.
2 as substring.
Mhm.
How would you?
How would you approach the question, has 0, 2, or whatever as a substring? If we have, think of just 0, 2 as a substring and nothing else. So if we just had 0, 2 as a substring, what could appear before the 0, 2? Anything. What can appear after? Anything. There.
But wouldn't that not be DFA?
I didn't say it's a DFA.
Oh, that's good.
What if I wanted to augment this to say, oh, it could be 0, 2, or it could be 1, 2. I think that's what it said.
Yeah.
Yeah, what about or 1, 2? What would I do here? Yeah, I just add another path. What if I wanted to have 0, 1 on top of this also? I just do the same thing. Is this a DFA? Oh, what is it? NFA. Oh, so we're stuck then. Or can someone bail me out? Oh, convert it to a DFA. Do we know how to do that? I know it's Wednesday. There are only 2 more days before the weekend. Okay, but yeah, we can convert this to a DFA. So if it appears hard to do as a DFA, what should you do instead? Make it an NFA first and then convert it over. So make it easy on yourself. Don't think too hard. If it appears hard to make for a DFA, just make it for an NFA. It's way easier, and then convert it over. Okay? Any other questions? Because we need to get to material stuff. Okay. So where are we? Yeah, Cap C, 351. Tempe, Arizona, United States, Earth, Milky Way. But where are we in the class? Yeah, so, but big picture things. So what did we see so far? Yeah, we made this DFA thing, and the reason for it is we wanted to model a simple model of computation that's deterministic, that we can implement. So what did we do with DFAs? We investigated, okay, well, we can make regular languages for them because that's a DFA for any regular language, because that's what a regular language is. So then we asked, well, okay, well, if I can make a regular language for a DFA for this language and a DFA for this one, can I do like the union or the intersection or the complement of one or the star or the concatenation or majority for the homework? We thought of many ways of combining things. So then we talked about what type of finite automata, not deterministic. What was the other one? It's the 14th letter of the alphabet. NFA, which is what? Non-deterministic. Why did we talk about that?
Because there are things you can't draw.
We'll get to that. But why did we make NFAs at all? Easier to do what? Yeah, to do concatenation and star. It was really hard to do it with DFAs. We didn't know how to do it. But we know how to do it with NFAs. So were we stuck then? Or how did we get closure under those two operations? We were able to convert back to DFAs, right? So then we talked about regular expressions, and then we found out they also recognize the regular languages because I can convert from an NFA to a regex and the other way around. So you may be thinking, okay, well, isn't every language regular? That might be a question you may be thinking on a Friday night. Is every language regular? So it could be. So here's my quote-unquote proof. So do you think my proof's going to be correct? No. So here's my proof. Yeah, obvious. So let's just say I have a string in mind, W. So W equals n characters. And I consider the language just that string, that single string, and nothing else at all. Just that single string. Okay? Can I make a DFA for just that string and nothing else? Yeah. Can I make an NFA for it? Yeah. Okay, cool. Great. So we know we can make an NFA or a DFA, I guess, for a single string. Okay? Well, what kind of closure did we get? Did we get closure under union for regular languages? Yeah. So is this singleton language, the language with one string in it, is that a regular language? Yeah, why? Because there's a DFA for it, or an NFA. So if I take two singleton sets, a language with one string here and a language with one string here, and I union them together, is the result regular? Yeah. So let's generalize. So let's just say we have, we're given an arbitrary language, if I can spell language, language L, and so let's get rid of the L before, and let's just consider an arbitrary language L. And what we're going to do is, you can think of L, any language, just any language. You can think of it as the union over every single singleton set. So you can think of this as, I'm going to look at every string in the language, and I'm going to union with the singleton with that single string in it. So look at every string in that language, make a singleton set from it. I know each one of them is regular because it's just a set with one string in it. I union all of them together, and then therefore, and that's the entire language. That's another way of writing the language. It's just a union of a bunch of singleton sets. Okay? Well, let's see. Well, each one of these sets, is it regular? Each individual set, is it regular? Yeah. Well, we have closure under union, right? Right? So, therefore, we can conclude this entire thing is regular because we have closure under union. Okay? That makes sense, right? I'm not trying to fool you, even though I am. We have closure under union. So, therefore, L itself must be regular because it's just a bunch of unions to get it. So therefore, every language is regular. Class dismissed. What's wrong with that reasoning?
It's not only union.
Well, if we have union for two languages that are regular, the result is always regular. So what's wrong with this? What does the union do? So if we take a DFA, for example, and another DFA, and we put them together, I get some number of states. That's more than the originals, right? So what if the language was infinite in size? How many states would I have this way? Infinitely many. Do you know now why we only talk about finite automata and not infinite? Because if we had infinite, then every language is regular. But we only talk about finite for a reason. So if L is finite, what can you tell me about it? It's just a finite language. So there's no tricks here. Is it regular? Oh, so every finite language is regular. That's pretty cool. So if we have some finite set of strings, I can make a DFA for each one, for any of them I want. It might be a ginormous DFA, but I can make a DFA for each one of them, and any finite set at all. But if we have an infinite set, that's where it may fall apart, or at least this reasoning might fall apart, right? Because I can't do infinitely many unions here, because then the size of the DFA will be infinite, and I'm not allowed to do that. Okay, everyone see why this is a problem? Any questions on my reasoning? Okay, well, let's try to investigate the question, whether every language actually is regular. So this approach doesn't work in showing that every language is regular or showing any language is not regular. Does that imply anything? That this one approach doesn't work, therefore there are languages that are not regular? Does that imply anything? Because this one method didn't work? No, just because one method doesn't work doesn't mean anything, okay? And in fact, we're going to see an example of that in a second. So let's consider this language. Let's see. Let's do this one. So you may want to, if you're trying to compute statistics on a set of data. So I give you a bunch of data, and you want to compute some statistics on it. So you may want to know, for example, so the inputs I'm going to give you are a bunch of zeros and ones. So just a binary string. And you may want to know how balanced that string is. And by balanced, I mean how close the number of zeros is compared to the number of ones. So you may want to know, for example, maybe these are votes. And you want to know whether a tie break will hold. whether a tiebreak actually holds. So you may want to know a DFA for this language. So all the binary strings such that the number of zeros in W is the same as the number of ones in W. So you may want to know something about that language and whether we can make a DFA for it or not. And if we can, how small can we make it, all that stuff. What appears hard to use a DFA for this? Why might this be hard for a DFA? Well, the set 0, 1 star is infinite, and we can make it a DFA easily for that.
Keeping track of the count.
Yeah. So what does a DFA remember? It remembers the state that we're in and the transition that we take, right? If we take a transition and we go to this other state over here, does it remember the state that it went from previously? No, it has no recollection of that because we're only moving through the input forwards. We can never move back. So it seems hard because as we're moving along, I need to keep statistics on how many zeros I've seen versus the number of ones I've seen. And it could conceivably happen that at some point we see a bunch of ones in a row, and then sometime later we see a bunch of zeros in a row to make the count catch up. Well, you can think of possibly avoiding this issue by saying, oh, I'm going to store the differences in the state themselves. So I'm going to have a state that corresponds to the numbers match up, and then I'm going to have a state that corresponds to there's exactly one more one than zeros I've seen, and then another state for exactly two more ones than zeros, and then etc. So what's the problem with doing that by storing the differences in the states? Well, it can't be infinite. It could be arbitrarily big. Yeah, so not infinite, but it could be as big as you want. So, so therefore this language is not regular. Is this language not regular because of that reasoning? No. Again, just because one idea doesn't work doesn't mean that the answer's not true. In fact, consider this language. So it's the same thing, except we consider 0 ones and 1 zeros. So the same number of 0 1 substrings as 1 0 substrings. Very similar language. However, the first one will eventually be shown to not be regular, and the second one is regular. So just because the counting argument appears to make things difficult, that doesn't prove that the language is not regular. In fact, it very well can be. And in fact, the second example was that question on the homework, the one that we just did. The one that had the same character at the beginning as the end. Instead of thinking of 0, 1, 2, think of 0, 1. If we have a 0, 1 somewhere, and the same number of 0, 1s and 1 zeros, then I must see a 1, 0 at a later point. So that must mean that the start and the end's the same character. So I disguised that question, as this one. So just be careful by saying just because one strategy doesn't work doesn't mean all strategies can't work. What we need to do to eventually show this language L to not be regular is we need to prove that it's not regular, that no DFA at all could have this language L. Okay? Does that make sense? I see one nod out of 50-something. Is that a good thing to do? And we're up to 2. By induction, we'll get to all of you. But yeah, so great question. How do we do it? How do we prove that this language is not regular?
Sorry, go on.
Try every DFA. How many DFAs are there?
Infinite.
Infinitely many. You guys have infinite amount of time, right?
Yeah.
Yeah, okay. We could work all in parallel, and then we could eventually, yeah. Okay. So we need a more comprehensive idea. Well, let's see. Maybe we can try to arrive at understanding when a DFA can't have a language by looking at things a little differently. So let's look at it at a different angle. Let's just suppose by contradiction. You guys know what proof by contradiction is, right? What is proof by contradiction? Suppose the opposite is true, and then eventually what happens? Then eventually we should get some kind of contradiction. So therefore our supposition that the opposite is true is false. So therefore the original statement is true, not the opposite. So let's just suppose that there is a DFA for this language. I don't know anything about what it looks like, but let's just suppose that there is a DFA for it. Let's just, suppose there is a DFA for it. So here's the start state. I'm actually going to make this a little bigger. So here's the start state. And let's consider this string. So let's just say that there are some final states in here. Doesn't really matter. And I'm going to put a state in the middle up here. Make the start state a little bigger. And let's feed it in this string. And here, I'm going to say that there are some number of zeros and the same number of ones as zeros. Okay? I haven't told you the number of zeros yet for a reason, but let's just say that this is a sufficiently long string. So it's a long string, let's just say. And so tell me first off, is this string going to be accepted by this hypothetical DFA? Yeah, why? Because it's in the language, right? Yeah. So that's perfectly fine because it's in the language. This DFA supposedly has that language, and it'll land in the accept state because it has that language. Great. What if I removed a 0 off the front and I did not remove a 1 at the end? Will it be accepted? No. If I removed 10 zeros off the front, suppose there are more than 10 zeros. If I remove 10 zeros and no 1s, will this string be accepted? No. Right. Correct. Because the number of zeros and 1s does not match. Does that make sense? Cool. So let's restore the original string. Well, I don't know what happens, but let's just say that this string has, let me ask you a question I've asked before. If we haven't read a single character at all, how many states have we seen? We've seen one state, the start state. If we have read one character, how many states have we seen? Maybe repetitions, but total number of states. 2 states. The start state and then wherever we went on the single transition. If I have n characters on the input, how many states have I seen? N plus 1. What if this input has, so let's just say that this DFA here has n states. And let's just say that this string that we consider has n zeros and n ones. So how many states will I see on this input total? 2n plus 1. Is that more than the number of states? Ooh. More states than there are states. Tim and Eric moment, right? So if we feed this string into this DFA, I'm going to see more states than there are actually states in the machine. More pigeons than pigeonholes. What am I referring to? Pigeonhole principle. What does that tell me about this DFA here? Does that tell me that I must see some state twice? Yeah. Well, if we saw every state exactly one time, that can't be possible because there are only n states here, and there are more characters on the input. We'll see more states as a result of the input size than there are actually states. So that must mean there is some state somewhere we saw twice at least. Okay? Any questions about that? This is the part of the material where students' minds explode. So if you have any questions at all or are confused on anything, tell me. Or if I need to slow down or what, yeah.
Is the 2n plus 1 gonna, well, you said we'll see each state once.
Yeah.
Or twice, sorry.
Yeah.
So what about the 2n plus 1?
Yeah. So it'll turn out that as long as the input has length at least n, we're okay. I picked n here for both pieces because I don't want to deal with the n over 2 issue because then I'll have to take floors and ceilings. This just makes it easier. As long as it's at least n total, we're okay. Yeah. It'll turn out, if we have n on both pieces, it's way easier to prove. But it can be proved both ways. Other questions? Okay, cool. So some state somewhere must have repeated when I fed this input in because of the pigeonhole principle. Let's say it's this state right here. Now, it very well could be the start state. It could be the final state that it ends up in. I don't know what that is. I'm just assuming this is one of the states along the way. Well, what happened? Well, what happened was, well, it could have repeated other states along the way, but what must happen is through a series of transitions from the start state, it eventually ended up at this state in the middle. Okay, it eventually got there. Well, what happened after that? Well, what happened is that state got repeated. So what must have happened is it must have came out of that state and came back through a Christmas tree type structure. Right? Because that state repeated. It could have been a single transition, or it could have been a whole sequence of transitions eventually leading me back to the same state. Well, what happened after that? It may have taken that thing many times. Let's just say we're done doing the loopy thing. What eventually happened? It must have done some other set of transitions to go to some final state. Was this string accepted? Yeah. Does it have the same number of zeros as ones? Yeah. So eventually it must have went to some accept state somewhere. Let's just say it's the one on the top right for convenience. Now, this is just an artist's conception. There could have been loops in the middle here. It could have repeated, all three of these states could have been the same state, possibly. So I'm not assuming anything here. I'm just making it look pretty. It could have looked very different than this. Well, it read some sequence of characters to get to this middle state, right? So I'm going to call that piece X. So the string that we have read along that first bit to the repeating state, I'm going to call it X. Okay? Well, the thing on the loopy part for the state in red, Could that be the empty string? It's a DFA. So there must be at least one transition that occurred. Could that transition be empty? It's a DFA. So there's no epsilon transitions, right? So there's some string that happens there nonetheless. So there's some string that happens here. I'm going to call it Y. That happened along the loopy part because this string is so long. And what do you think happened on, what do you think I'm going to call the last little bit? Z, good. Notice the pattern? So Z is going to go here. And I'm going to call the original string W for to keep it short. So we can conclude from this that the original string W is just XYZ, because it's just reading the X part, reading the loopy part on the Y part, and then the Z part after. Anyone have any questions on that whatsoever? So is this string in the language? I think I've asked this 3 times, but is this string in the language? Yes, because it has the same number of zeros and ones. What if I took out the Y part? Is this the string XZ still accepted? Yeah, because it's a DFA. Remember, follow the X path to get to that red state. Just ignore this and then just continue along the Z path as you did before. Oh, did we end up in a final state? Ah, so we end up in a final state. So it must be in the language. What about if I did Y twice? YYZ. Anyone a Rush fan? YYZ? Never mind. Yeah, so that's in the language too. Oh, what if so this is notation. What if I did Y I times? So what this boils down to is Y repeated I times. Is that in the language too? For any I at least 0? Yeah. What if I equals 0? I pick a string 0 times. What is the string picked 0 times? The empty string. Okay? So if I pick a string 0 times, it's the empty string, which is the XZ case above. Oh, okay, that's pretty cool. So we found out if we feed in a string long enough, it's long enough string so that it repeats some state, then we can just repeat around that loopy part as many times as we want, and we can infer a lot of information. If we know one such string, we know infinitely many strings this way that are accepted. So if we know one string like this, we know infinitely many others that are accepted too. Okay, well, let's see. What did we infer about the Y string? Just the Y part, the loopy part. Could it be the empty string? No, because it's a DFA. Can DFAs have epsilon transitions? No. So we know, so this is one thing we'll note. The second thing we'll note is that the Y cannot be the empty string. Could it be a single character? Yeah, it could be. But it can't be the empty string because it's a DFA. Cool. This is actually enough to get to what we need to go, but we're going to actually go one step further. So notice when I said that there could be many loopy parts along the way. Will this reasoning still hold if we instead just consider the very first time it loops? So instead of just this arbitrary time in the middle, what if we just consider the very first time it loops? Will the reasoning still hold? Yeah, if we find some loopy part in the middle, at the very beginning, as far in the beginning as we can, then we can just go around that loop as many times as we want and then continue on our way. So let's just think about when the first time it loops occurs. Well, how many states are there? N. Well, let's see. It could be that the very first time it loops is after we've seen every single state in the entire thing. So it could be that the X part goes through a lot of the states, and then the Y part goes through all the other states before it eventually comes back to itself. So we could visit every state along this way. But what does that tell you then about the length of X and Y together? So X and Y together correspond to the beginning part and then the first time it loops around. That can't exceed the number of states because we're considering the first time that it loops. So that infers, what we can infer from that is that the length of X and Y together is at most N. The length of the string X with Y right after it, the Y, remember, is the loopy part, that can't be more than the number of states because we're considering the first time we loop around. We come back to, we go from some state and do the Y part and come back to the same state. So we can actually infer quite a lot of information from this, but any questions? Yeah.
So the length of X and Y could be equal to the number of states?
Yeah, it could be. It very well could be. But we know it can't be more than that because there are only n states. And if we consider the first time it loops and that there's no state repeating at all along the way because it's the first time, then it can't be more than the number of states that there are. So together they can't exceed the number of states, but it could be the number of states. But we don't know that in general. Well, let's see. Wait a second. Did our reasoning right here have anything to do with the 0-1 string? The string, or the language with the same number of zeros and ones? Did our reasoning have anything to do with that whatsoever? I came up with an example of like removing a 0 and showing that it can't be accepted, but does this reasoning hold for any regular language? I got a no, I think one yes, and no maybes for improving. Does this reasoning hold for any regular language? Well, let's see. If we have a regular language, does there exist a DFA for it? Yeah. So if we feed in a string long enough, will a state be repeated at some point in any DFA? Yeah, because there's a certain number of states, and if I feed a string long enough, some state will repeat. It might be the start state, it might be the final state. We don't know. But some state will repeat. So, in fact, just from that reasoning, a state will repeat, that's enough. Because, by the pigeonhole principle. And because it's a DFA, the looping part is not empty, and there is some first time that we actually repeated. Okay? Any questions? So let's actually take a break and then prove some awesome things.